Good God. Okay, here we are. So energy-bearing nutrients. There are 3 of them, which are carbs, fats, and proteins. Essential vitamins and macro, well, ions, let's call them this way, chemicals. End products of carbohydrate digestion are monosaccharides. Where do you get galactose? Galactose, where do you get it from? It's a product of lactose breakdown, so it's milk. Fructose, here in America, you can get it directly from food if you eat the staples of American healthy diet, which is called high fructose corn syrup. I'm just kidding, it's not staples. It's actually, it actually causes diabetes. So, or sugar, sucrose, yeah. But, you know, we don't like to beat around the bush, so we just get just high fructose corn syrup. And by the way, the lobbying efforts of the industry that produces it are pretty powerful. Getting it out of the foods is a big deal. It's still present. Monosaccharides are metabolized in the liver, right? Galactose is metabolized to glucose. Fructose can bypass. It can be converted to triglycerides directly. What are the main reasons processed food contribute that much to obesity epidemics in the US? It is good. That's basically the answer. Food is good, we are weak. Okay. But seriously speaking, high carbohydrate density and processed food is very palatable. I just had a package of peanut M&Ms and they tasted heavenly. Seriously. What are the end products of fat digestion? Glycerol and free fatty acids. Chemical difference between saturated and unsaturated fats. Saturated are solid and they all carbon-to-carbon bonds are saturated. In non-saturated, there is 1 or more double bonds in the molecule. And non-saturated are liquid. Solids are going to be found in animal fat. Liquid are going to be found in plant fat and fish. Cholesterol you can find practically, in the animal fat mostly, in animal food, and especially in the egg yolk. Fats and cardiovascular disease. What I want you to know, there's no demonstrable association between the dietary intake of saturated fat and the risk of cardiovascular disease. But trans fat, which is the product of partial hydrogenation of plant oils, significantly increases the risk of cardiovascular disease and e.g. atherosclerosis. Does that make sense? Just basic trans fats are bad. End products of protein digestion are amino acids. What are essential amino acids? Please do not memorize them, I beg you. You have to understand that essential amino acids are the ones we have to get with food. That's it. Okay? Protein that comes from animals is a complete protein. You know, everything is there. Vegetarians have to combine nuts and vegetables, or legumes and vegetables, to get a complete diet. All 21 amino acids. High protein diet leads to acidification of the blood, and if you do not supply your diet with sufficient amount of calcium, that may lead to the weakening of the bones. All or none rule means that you need to get all amino acids to make any protein. So when you For the muscle mass gain, you need not only protein but also carbohydrates to provide sufficient amount of energy. Which nutrient? Carbohydrates, right? If this nutrient is absent, what proteins are going to be used for? If you just eggs, just egg whites, make it simpler. You just egg whites, breakfast, lunch, and dinner. What this protein is going to be used for? Energy. Yep. Positive nitrogen balance when protein intake is more than protein catabolism, basically. Protein anabolism is more than protein catabolism. When you take in more nitrogenous nutrients, amino acids, then you excrete urea, which is the product of protein breakdown. What are vitamins? Cofactors for enzymes. In terms of vitamins, I will be very, very clear what vitamins you must know. Deal? You have to know by exclusion. So lipid soluble A, E, D, K. 4. Are we good? Pathologies. 4 fat solubles. When I say main functions, I refer to pathologies. Okay? You get rid of vitamin A, you get night blindness. Sorry, at this point my tongue practically cannot move. Night blindness. You get rid of vitamin D, rickets. Those are 2 I want you to know among fat soluble. Bless you. Vitamins B and C. I want you to know that if you get rid of B1, it's beriberi, neurological disorder. You get rid of vitamin C, it is scurvy. You get rid of vitamin B12, and it's going to be anemia. That's actually, I'm going to write it down, it's called pernicious anemia. Vitamin B12 is necessary for the cell division. When red blood cells produce, they produce because of rapid cell division. If there's no vitamin B12, no cell division, you're bound. Does that make sense? Microelements. Sodium, potassium, chloride, sulfur, that kind of stuff. Basically, if you see something exotic like selenium, okay, that's going to be a microelement. I'm going to be very distinctive in those types of questions. When you don't have calcium, focus on calcium. When you don't have calcium, what's the problem? Bones. When you don't have sulfur, it means that you don't consume enough protein, really. You cannot possibly go low on potassium. When we get to the renal, give an example, like you eat a banana, immediately your kidneys have to excrete all the potassium that you just put in the body. Okay? Immediately, right away. Problems with sodium, you cannot go low on sodium unless you decide to survive on distilled water. In this case, you're not going to survive for long, so, pretty much death. Magnesium, neurological problems mainly. Chloride, the same. Iron deficiency. For iron deficiency, when we run low on iron, what happens? Anemia. Fluorine, teeth, right? Zinc, copper, screw that. Iodine, thyroid. Okay. One of the interesting symptoms, just FYI, one of the interesting symptoms of zinc deficiency, do you know sometimes on the nails, you have white patches. It's associated with zinc deficiency in a diet. Okay, catabolism, degradation, anabolism, synthesis. Exergonic produces energy, endergonic consumes energy. Catabolic reactions are usually exergonic. Anabolic are usually endergonic. Why the efficiency is not 100%? I mean, we can go into the second law of thermodynamics if you want, but basically we lose some energy to heat all the time. It's actually good. Okay, let's do this review. Okay, what happens in glycolysis? You start with how many carbons? And then it's converted into two pyruvates, right? In the middle, there's phosphorylated intermediate, glyceraldehyde 3-phosphate, right? Now, pyruvate, what can happen to it in the absence of oxygen? Fermentation. Pyruvate will, is it going to be reduced or oxidized? Reduced to lactic acid. Okay? Does that make sense? So final electron acceptor in fermentation is pyruvate. Where does it get electrons from? Which molecule? NADH. So you have two NADH produced and 2 molecules of ATP, right? It's glycolysis. Good? What is the final electron acceptor for oxidative respiration? Oxygen. What is the role of hydrogen ions in oxidative respiration? There are 2. One, they compensate for the charge. Electrons are negatively charged, hydrogen ions positively charged, compensate. Second, diffusion across the membrane provides directly provides energy for ATP synthesis. We good? Okay, where in the cell glycolysis happens? Cytoplasm. 3-carbon intermediate glyceraldehyde 3-phosphate. Final products of glycolysis in the presence of oxygen. Pyruvate, NADH, ATP. Without oxygen, pyruvate is reduced to lactate. Does glycolysis produce a lot of ATP? No. Pyruvate go into the transition step. Are we good? Transition step. What happens to pyruvate? C3 becomes acetyl-CoA, right? 2 carbon. Where does extra carbon go? How does it leave? In the form of CO2. What is produced? It's very important. N word. NADH. Good. NADH. So 2 carbon intermediate, this one, acetyl-CoA. Where does it enter? Krebs cycle. And forms 2 plus 4. I'll call constants 6. Yes, I'll call math professors now, if you can put 2 and 4 together. So that's citric acid, okay? Citric acid is oxidized to 5 carbon intermediate, right? Losing CO2, and eventually this, you have to understand that this, first of all, I do not require you to memorize alpha-ketoglutarate acid, succinyl-CoA, succinic acid, formic acid, malate fumarate. No. What I want you to understand is that alpha-ketoglutarate does not immediately become oxaloacetate. There are many steps here. Does that make sense? But CO2. So transition step and Krebs cycle, how many CO2 molecules you get? Total. Transition step and Krebs cycle. 3. So how many Krebs cycles per glucose molecule? 2. 6 molecules of CO2, meaning that the entire glucose is now oxidized. Good. What else do we get in Krebs cycle? Per molecule of glucose. Per molecule of glucose. So 6 CO2. Okay. Krebs, 6 NADH. What about transition step? 2 more. Think so. Transition step 1, Krebs cycle 3, total of 4. But since we have 2 pyruvate molecules, does that make sense? Do I make sense? This is kind of okay. So 8 molecules of NADH. What else? 2 molecules of ATP and 2 molecules of FADH2. That's per molecule of glucose. Does that make sense? What happens to these guys? Where do they go? See again? Electron transport chain. What do they do in the electron transport chain? Okay, electron goes away and NADH becomes NAD+. And also hydrogen goes away, right? What does electron transport chain do? They drive hydrogens across the membrane of the mitochondria using energy of electrons. Okay? So hydrogens have this gradient, okay? And what do hydrogens do? They go through the ATP synthase, they diffuse, correct? And when they diffuse, they release energy and have ATP produced. How many molecules of ATP? I'm going to show you a little trick. So, I don't know if you ever wondered how do we calculate, how scientists figured out, what is the... So, first of all, theoretical efficiency of oxidative respiration. How many NADH molecules in total we have? 2 plus 8 gives us 10. How many FADH2 molecules? 2. How many ATP molecules were produced in glycolysis and Krebs cycle per glucose? Total, huh? No. Glycolysis, how many ATP molecules per 1 glucose? Say again? 2, yeah, absolutely, 2. And during Krebs cycle, another 2. So total of 4, right? So already have 4 ATPs. Turns out that FADH2, each molecule of FADH2, can give you 2 molecules of ATP. Yes. Okay? So it means 4 ATPs. And each molecule of NADH carries enough energy in electron form to give you 3 ATPs, which means 30. The total yield 38. Does that make sense? This is pretty cool. I wanted to say something smart. Oh, we never get 38. You know why? Turns out, remember the idea of that membrane? So you have a lot of hydrogens here, little hydrogens here, and then they diffuse through the ATP synthase. Turns out this membrane is a little bit leaky. So some of those hydrogens, they trickle down bypassing ATP synthase. Does that make sense? Like in that analogy with the water mill, imagine that pipe that runs water to the wheel, it's leaky. Some of that water just trickles down. That's why we never get 38. It's about 32, 34. Okay? That makes sense. So we got this. Why hydrogen ions cannot diffuse across the inner membrane of mitochondria? Because they're charged. What allows them to cross the membrane? ATP synthase. What is the role of this process? Process is chemiosmosis. What type of energy conversion? It converts kinetic energy into the chemical energy. Does that make sense? Right? Final electron acceptor for electrons in oxidative respiration. Come on. You got to be kidding me. Oxygen, right? It's oxygen. Where do hydrogens go? They make water. Look. That's what happens at the end of oxidative respiration. Electrons, hydrogens, oxygen, and you get water. Fermentation, it's pyruvate. What does it happen? This is not even English. Oh, when does it happen? When there's no oxygen. Okay. Final ATP numbers for oxidative respiration for molecule of glucose, 30-something. And that's ballpark that you kind of have to know, like 30-something. How many ATPs in fermentation? 2. 2 ATPs for fermentation, that's it. Can cells store ATP? No. So when ATP levels in the cell go up, what happens to glucose? It's converted to, first, glycogen in the process called, not going to help you. What? Glycogenesis. Okay, you have to know that. Come on. Glycogen storage, is it unlimited? Well, of course it's limited, but it turns out it's very limited. You don't store a lot, and only liver and muscle. Okay, that's it. So when glycogen storage is at the top, and you still have glucose coming, what is it converted to? Fat. Now, okay, fat. Fats, how is it synthesized? Which metabolites? So you have glucose, right? And it's converted to pyruvate, which is converted to acetyl-CoA. Okay? So how do we make fat? What do you use? What do you need to make triglycerides? Glycerol, solarol, FFA. Where do you get glycerol from? you need to make fat. You're making fat. So you can't get it from fat. Otherwise, it's like pointless. You're making fat. Where do you get glycerol from? Which process? Glycolysis. You convert G3P, glyceraldehyde 3-phosphate, into the glycerol. Where do you get free fatty acids from? Acetyl-CoA, you run beta oxidation backwards. And then you combine them in triglycerides. We're good? Is that clear? Cool. Now, when you're starving, what happens to glycogen? No, glycogen, just glycogen. What happens to glycogen when you're starving? We get to ketosis. Breaks down to what? Glucose? Come on, I'm not asking like horribly complicated biochemistry questions. Glucose, right? For which organ? Mostly. Brain. That's your primary glucose utilizer. You run out of glycogen. What's going to happen next? Okay, we'll get to the fat. You're right. Ketone bodies. But ketone bodies are formed because oxaloacetic acid from Krebs cycle is used for what? Gluconeogenesis, which is what? Synthesis of glucose from scratch. Are we clear about it? We're good? That's really, if you ever ran long distance, that's hitting the wall. Lipids, more dense, right? How can this energy be recovered from a molecule of triglyceride? Okay, so what happens to fat during the process of, how do we call the fat breakdown? Breakdown. Lipolysis. How do we call it synthesis? Lipogenesis. So during lipolysis, what happens to the molecule of fat? So we've got the breakdown of triglyceride to free fatty acid and glycerol. Glycerol is converted to G3P, right? And FFA are converted to acetyl-CoA. How do we call this process? Remember what beta oxidation is. I'm not going to ask you about the mechanism. Don't worry about it. Okay? No mechanism, but know that beta oxidation is the breakdown of free fatty acids in the mitochondria. Are we good? Is that clear? So it's this part, really. It's kind of boring. Okay? It's kind of boring. Acetyl-CoA and G3P, where does glycerol come from? G3P, fatty acids come from acetyl-CoA. Yeah, so that's pretty much a discussion of what we showed right here. Now, what is used first as the source for glucose in case of fasting again? First, before fat, liver and muscle cells, glycogen. In the process of glycogenolysis, we run out of glycogen, then fat. So fat will be broken down to glycerol, free fatty acids, acetyl-CoA, G3P. You've got the whole shebang, right? But what if you're totally fasting and you run out of glucose? What's going to be used as the glucose precursor? Which molecule from Krebs cycle? Oxaloacetate. If you use up all oxaloacetate, which step of glucose metabolism is going to shut down? Krebs cycle. No Krebs cycle. Does acetyl-CoA have anywhere to go? No. What is it converted to? Ketone bodies. In where? Organ. In the liver. Ketone bodies are used as the fuel source. That's ketogenic diet. Basically, it's a extremely low carbohydrate, high fat, high protein diet. Oh, God. I had so many things coming through my mind right now. Okay. Yeah. Based on what we discussed, which diet would be more suitable for weight loss? High fat, low carbohydrate. What are the benefits of high fat, low carbohydrate diet in relation to the insulin levels? You have a lot, very little glucose. What happens to insulin levels? They stay low, right? They stay low, and it's good because you don't develop resistance. You know, lean body mass, percentage-wise, you become leaner. You're not going to get bulky, but you become leaner. Type 1 diabetes versus ketosis, what's the difference? Ketogenic diet versus ketogenic diet. What's the difference between type 1 diabetes without insulin and ketogenic diet? When you're not taking insulin and you have type 1 diabetes, your cells are going to use what? Fat. They're not going to be able to use glucose because they can't uptake it. Does that make sense? So they use fat. They produce a lot of ketone bodies, okay, because they shut down Krebs. They need to make glucose. Gluconeogenesis is stimulated. Krebs is shut down. Okay, they have a lot of ketone bodies. Why you don't go into the ketotic coma when you just eat fat? Answer is simple. It's not as fast, and your kidneys can get rid of the ketones, can regulate pH. When you don't have access to insulin, the whole change happens so abruptly that pH drops very, very quick, and it shuts down the brain. That's the whole difference. Controlled versus uncontrolled. Cholesterol, what do we use it for? Mostly steroids. Steroids, bile cells, yes. Where is it coming from? Inside or outside? Inside. How is it transported in the blood? How fats in general are transported in the blood, including cholesterol? High density versus low density lipoproteins. Low density lipoproteins, again, they carry fat from liver to tissues. High density tissues to the liver. Why they high density, for instance? Because high density lipoproteins have much higher protein content. What do you need to look at when you do cholesterol levels assessment? Ratio of LDL to HDL rather than total cholesterol. So ratio is correlated with the level of cardiovascular disease. If you have a lot of low, very little high, is it good? A lot of low density lipoprotein and very little high density lipoprotein. That's bad, right? When you get the opposite, that's good. A lot of high density lipoprotein, very low. Basically, I mean, I can tell you, for me, I'm kind of bragging. I do not look for cholesterol-free food, quite an opposite. I eat a lot of eggs, for instance, a lot of meat. But when last time I did blood work, my cholesterol, total cholesterol, was right at the top. It was hitting the ceiling. So basically, the recommendation is, I think, like 200 or some 100, whatever. I was at that level, maybe 0.1 lower than that. But my levels of HDL to LDL, or whatever the ratio was, whatever was in denominator, it was awesome. A lot of HDL, like 2 or 3 times more than recommended. So I don't worry about total cholesterol. Does that make sense? And that's what more and more should be looked at. Saturated fats, if you eat a lot of them, really a lot, they will increase cholesterol synthesis. But other than that, no. Unsaturated generally decrease the cholesterol levels in the blood, especially LDL levels. Trans fats massively increase the amount of LDL. Dietary cholesterol and plasma ratio are not linked. Forget about McNamara paper because we did not really discuss it. Proteins, what happens to them? When they're broken down to amino acids, what happens to amino acids? First and foremost, amino acids are absorbed in the blood. What happens, and then they get into the liver. What happens to amino acids in the liver? How are they catabolized? First, transamination, right? So you get glutamate and some keto acid. Glutamate can be deaminated and eventually produce CO2 and urea. And that is pretty much oxidation and yields energy. Keto acids, okay? Deamination, you have breakdown of glutamate, products of, well, okay. Okay. What I mean by this is you have amino acids, they become keto acids, and keto acids can become what? Can enter Krebs cycle, or some of them can become pyruvate. Does that make sense? Remember that final flow chart that I showed you, metabolism of different chemicals? You have to be able to kind of draw it. And I strongly encourage you to draw on the exam as much as you can. What's more, it's not cheating, I do not consider cheating, but when you get exams on Monday, if you want to draw something right away while you remember it, go for it. Like clear. Like, you want to draw that flow chart and just keep it in the back? Sure thing. You want to draw the chemical reaction for like bicarbonate and hydrogen ion production? Go for it. You want to draw any flow chart for, I don't know, gastric regulation, stuff like CCK, secretin, whatever. Draw it. Do it first. Okay? So you can use it later answering the questions. Am I clear? I encourage you to do that. That's fine with me. I want you to be able to analyze, not memorize. I know that you can memorize. If I will ask you to memorize the phone book for the exam, you will memorize the freaking phone book. Metabolic changes associated with the dietary changes. What I mean is, if we stop eating carbs, what's going to happen? I mean, what's going to be the switch in terms of metabolism when you eat only fat? Does that make sense? Ketone bodies and so on and so forth. Absorptive state. When is it observed? Absorptive state is after you eat. Which hormones regulate absorptive state? First and foremost, insulin. Leptin is produced, giving you a sense of satiety. You have to understand what happens. Like glucose, stored as the glycogen in fat, used as a metabolic fuel. Fat, stored as fat, used as the metabolic fuel. Protein, what does it do? Amino acids, Amino acids get into the cells used as the building blocks for protein synthesis. Does that make sense? During absorptive state, amino acids are mostly used for protein synthesis. Does that make sense? Are we good? So if I'm going to ask you which processes are stimulated. So what is increased in absorptive state? G words. Glycolysis and glycogenesis. L word. Lipogenesis. And protein synthesis. Okay. So does that make sense? Insulin. Now, based on that, inhibited glycogenolysis, gluconeogenesis, lipolysis. Post-absorptive state. Observed when you are fasting. Main metabolic purpose. What I mean by that? Which molecule is required when you're fasting by your brain? Glucose. So, in the liver and skeletal muscle, what happens to glucose? Sorry, not to glucose, to the fat. In the liver, skeletal muscle, to the glycogen and fat, what happens? During post-absorptive state. Lipolysis, sorry, I didn't hear. Lipolysis and glycogenolysis. That makes sense? Breakdown of glycogen. Glycolysis is totally blocked. Gluconeogenesis, kidneys and liver. Adipose tissue, lipolysis. Proteins, what happens to proteins? Are they used as energy in post-absorptive state? Sure, why not? So kidneys are responsible for gluconeogenesis. What is glucose sparing? All organs except brain use ketone bodies as the fuel source to spare glucose for the brain. Good? Can brain use anything else? Yes, ketone bodies, but that's extreme. Pretty much it can, but it prefers not to. Which hormone regulates post-absorptive state? Glucagon, right? That we discussed. What controls food intake? Hypothalamus. Sensation of hunger is increased by ghrelin, right? And appetite is inhibited mostly by leptin, also by CCK. Elevated levels of amino acid and glucose in the blood, they also inhibit appetite. BMR. This is pretty straightforward. Which of these decrease BMR? Old age. Lower BMR is in females. And that's it. If you increase any of other 8 left, that will increase BMR. Does that make sense? What is the thermostat? Hypothalamus. Core temperature is inside, shell on the surface. Mechanism for cooling, sweating and dilation. Mechanism for heating, shivering and constriction. Heat stroke. Remember, so when heat stroke hits you, what happens? Body temperature increases. What happens to the hypothalamic activity? What happens to the hypothalamus in the heat stroke? Your thermostat gives up. Body temperature increases. Hypothalamus doesn't regulate it. BMR increases. Body temperature increases, which increases BMR. Increased BMR increases body temperature. Increased body temperature increases BMR. Positive feedback, heat stroke. In hypothermia, hypothalamus activity is also depressed. So anything that would heat you up isn't done. You would progressively cool down. Okay? Fever. Now, with fever, what happens to your thermostat settings? You change, yeah. Your thermostat setting is increased. You have new normal. So why do you shiver when you have fever? Yeah, to get to this new setting. Okay. Why do you look pale? To increase temperature, to save some heat. So when I say what's the role of fever, some microorganisms do not replicate well, and it sequesters iron. Very, very important for bacterial diseases. Iron becomes less available. Bacteria cannot reproduce as effectively as they used to, especially if they're in the blood. Does that make sense? Any questions?